You can just text him back everything important I said. Shouldn't take too long. Sorry about that, starting late for the broadcast. Thank you, whoever it was that texted in to tell us that we weren't actually sending this out. I think I just basically reviewed the fact that I'm technically incompetent, that I forgot to charge my microphone earlier, so I've got a Bluetooth thing in my ear, that I hope you guys can hear me with the Bluetooth thing in my ear because it's really annoying to have it in there. And that stress is pushing on something, and that strain is what happens when you push on something. And that stress and strain are important in CNC machining, partly because it impacts how the chip forms on the edge of the tool. But in reality, what we're going to talk about today is how it impacts our ability to do fixturing. So fixturing is the way we hold things in the machine tool, right? It's so in lab, what have we done for fixturing so far? How have you guys held stuff in the machine tool in lab? Yeah. So you've clamped something in a vise, and so that's you're really just you're putting a piece in between two parallel planes, and then you're using mechanical advantage through a screw to have those things tighten relative to each other, and it squishes on the part that you're clamping. How else have we held stuff in the machine tools? Yep. We've used a hydraulic chuck in the lathe. We have two different kind of hydraulic chucks in the lathe, depending on which one you're in. One of them is a 3-jaw chuck, so you've got 3 points that point towards the center, and they move out or they move in closer to each other. And it's hydraulic pressure that clamps those together, that holds them together. So we've used a hydraulic chuck in the lathe, or there's a collet chuck in the lathe, which still uses hydraulic pressure, but instead you've got a tapered cylinder and a tapered cone, or the collet piece that fits in there. It's the same taper on both pieces. So if you squish them together, the inside part will get squeezed together, right? It'll make it smaller. I mean, the outside part tries to push out too. So you make the outside part stronger than the inside part, and you pull it back. And as you pull it back, the tapers interact with each other. It squeezes it together, and it holds a round stock. Typically, we hold round stock in those kind of things. Turns out you can make the collet to be different shapes. So you can make square collets, and you can hold square stuff that way. Make octagon collets or hexagon collets, hold oddly shaped stuff with collets. But it's in both cases that we've talked about there, it's really friction that keeps the part from moving, right? And so what's friction force equal to? Not on the chip interface, but in general, what's friction force equal to? Normal force times mu. So and that clamping that we're doing is, whether it's in a collet where we're squeezing something around, or it's in a vise where we're squeezing parallel planes together, that clamping that we're doing, the friction that comes from that is really what keeps the part from flying across the machine tool when the cutting tool hits it, right? The cutting force, I mean, it actually might even be on this quiz. I have this quiz question where I asked the question, what is the force that keeps, so if you're drilling a hole or if you're facing a part in the mill, what's the force that keeps the part from flying up out of the fixture? Because the cutting force tends to, on milling operations, the cutting force tends to be partially up, partially sideways. It just has to do with the shape of the cutting tool, right? That spiral that's designed to pull the chips up out of the cut, but it also wants to pull the part up out of the fixture. And so I always had this question, and the answer I'm looking for is friction, because that's the primary force. And someone always nitpicks me and says, "What about gravity?" And then I always have to give them the point on the auto-graded quiz that marked them wrong because they were considering gravity. And so I think I either fixed the automatic grading on that question, or I deleted the question because I get tired of having to give people the point. But in reality, most of the force comes from the friction, unless what? When would it not be that most of the force is coming from friction? and the part's really heavy. You could, in fact, have a really heavy part and not clamp it at all and go do cutting operations on it. I've seen it happen on accident. Yeah. You know what? I'm going to go back, take points away from all those people. Because it still was, but I said pulling up. So it is gravity. Gravity is counteracting the up part of it. Yeah. You can all, yeah. That's why before we got to that type of fixturing, I asked this question. Because I was talking about clamping in a vise or clamping with a collet, then you're relying on friction. But you're right. You could mechanically fasten it. So one of the ways I like to do this, if I can, if I've got a really complex part, I can't clamp it on any of the sides or something, but it has holes in it. The first operation I'll do is make the holes. And then I can clamp it down using bolts to some sacrificial part. And so I can mechanically fasten it. Now, typically the fastener is smaller than the hole. And and so maybe we push it up against the fastener. And certainly if there's like a washer, that washer pushing down is keeping the thing from coming up. But typically, even in this mechanical fastening where we're clamping it down like that, we're relying on friction for the side-to-side resistance of the force. So friction is always going to be important to us. Getting back to my plastic question. So there's two reasons. One is we're doing that 3D surfacing stuff. If we want to make a complex, nice-looking, curvy part, you're going to take really small chips. And and it's because you want to index the tool over as little bit as possible, so you get a nice smooth curve, right? The shorter the line segments, the smoother the curve's going to be. So those little tiny chips, they go in the machine. If you don't clean them all out of the machine before you turn the coolant on, they get washed down into the coolant reservoir. They get through the filter. It's just a like screen mesh filter. They get through the filter. They have no trouble going through the coolant pump. Coolant pump could pump anything. Gravel, you could probably pump through the coolant pump. But they get up in the coolant hose that runs through the spindle, has all these right elbows in it and bends around 90 degrees and 180 degrees and comes out and points coolant at the part. Yeah, they get stuck in those elbows up inside the sheet metal. And then if you're lucky, you can hook up like an air hose to the nozzle part of the coolant system. You can blow most of those chips back down into the coolant reservoir. In reality, you have to take the sheet metal off the machine tool. You have to take the wrench out and undo the fittings and poke like a pipe cleaner through it or a coat hanger to clean that out. So that's the other reason we don't like plastic chips, for that reason. But the real reason we don't like plastic is that it's so damn hard to hold on to. So one of the reasons we love plastic for our design applications is because it's very low friction, right? Plastics tend to have slippery surfaces, and so we like slippery surfaces for low friction applications. The problem is if we're trying to clamp it in a vise or a collet, we can't impact the mu, right? We can't impact the friction coefficient. So all we can do is clamp harder. And when we clamp harder, because we know stress and strain, let's take a look at our vise fixture here. This is a good segue, huh? I knew what slide was next. Very proud of myself because I hardly ever know what slide is next. So we keep the part from moving by clamping, by forcing the jaws together. So we're applying a force over an area, right? So we can figure out the stress. That's pretty easy. We know what the stress is. And if we know the elastic modulus of the workpiece material, if we know the stress and we know the elastic modulus, we can know how much we're going to change that shape when we clamp it, right? So if we're clamping it and we make an oval pocket here, it's got some width to it, right? Yeah. Hide. Woo! Made it hide. All right. When we let go of the clamping force after we're done machining, the pocket's going to get wider because we clamped it tight, we machined it, we let go of it, we relieved the stress. So the strain goes the other direction, then it elongates when you relieve the stress. And so actually you can calculate how much it's going to change. So you can compare W1 and W2 as long as you know what the clamping stress was, what the elastic modulus for the material is. So that's cool. What could we use this knowledge for? Well, I guarantee it'll be useful for question 17 on the quiz. Might not be number 17. I don't know what number it is. So it'll be useful for answering that question on the quiz. But as engineers, what could we use this knowledge for? Why would we want to calculate this? Oh, it's going to be a bigger change in plastic than it is in steel for two reasons. The friction coefficient from steel on steel is way higher than the friction coefficient of steel on plastic. And so that means we don't need as much clamping force. And the modulus of elasticity is plastic is much more squishable than steel. Does that make it a higher or lower modulus? I think lower, right? Yeah, I didn't say, I just said more squishable because I couldn't remember if it was the top or the bottom of the equation. Because if I need to know that, I'll look it up, right? Google is your friend. You had a question? No. Okay. All right. So why would we want to calculate this? We've demonstrated that we can calculate it. The equation's pretty simple, and everybody in the room, once you understood the concept, could have derived the equation, right? Say yes. It'll make me feel better. Yeah, you all could have derived the equation. As engineers, we don't have to derive the equations. We can look them up in the book. But why do we want to? Yeah. You could program the machine to cut the hole undersized so that when you let go of it, it stretches to the right size. That's pretty cool. But you can't do that if you don't know. Now, is it going to work on the first try? Probably not. But you get pretty close on the first try, and then you can make some adjustments based on that try. So that's one reason that we want to know it. Now, what other, so clamping a part in a vise changes its shape. When we let go of it after we machine our features, it'll change shape. You guys make it this week, you're making pistons for your Stirling engines or thermoacoustic engines, right? So we used to actually run those engines. We had a flywheel we attached. And so we had a connecting rod. And so we actually relieved some material on the pistons on the side. And when we did that, if we did that secondary operation without clamping correctly, it took us months to figure out what the problem was. We would make a nice round piston. It would fit. It would work in the cylinder. Everything would be perfect. We'd put it in a collet fixture, squeeze it all together, make the secondary operation where we just relieved some material on the side so it looked more like a piston from a car. And then they weren't round anymore. We couldn't figure it out. We tried all different kinds of things. Finally, we started making the whole inside not round, so that when we clamped it and did the operation, it would become round. And it was partly because of this clamping stress, but really it was because we were removing residual stress in the material differently. We weren't taking it away uniformly across the diameter. And so that was causing the material from its internal stresses from the way that it was made to expand differently. We fixed that problem by getting rid of the flywheels. It also made for fewer parts to make an ME1800, which made ME1800 easier. And they don't have a lot of power when they operate. So trying to spin that flywheel made many fewer of the engines work. So fix that. All right. What else in machining operations? So this is obvious to you guys now, right? And it would have the same impact if you were clamping down on a part. It'll bend the part that way when you relieve it. A guy I know, he was the master for Boeing aircraft. So he worked for Boeing, he was an engineer at Boeing. He was the master at doing selective heat treating on these giant airframe parts to make them straight again after the machining was done. Because when the forgings would come in, and you might have a fixture that's from me to the wall, right? These big giant gantry mills ride around on a crane, basically, and the milling head comes down and does some machining over here and moves over there and does some machining. It's all the same physics of the stuff we're talking about, but the part might be 30 or 40 feet long. And the forging comes in, and the forging's really expensive. The forging might, I don't know, $100,000, couple $100,000, maybe $1 million just to get the part before they machine it. They put it in the fixture, and it doesn't quite fit. And what they do when it doesn't quite fit is they get like 5 or 6 fat guys to go stand on the end of it to bend it down into place so that they can clamp it in the fixture. And then they machine it. And of course, as soon as they release the clamps, it springs back to the shape it wanted to be. And so you could actually heat it up and cool it at different rates, at different places along the part, and make it relieve those stresses and come straight. So that was his job. He got paid an outrageous salary by Boeing. And he just went from factory to factory telling them where to put the heat to make this part straight again. I think that's art, not science. We can understand the scientific principles that allow it to happen, but knowing exactly where to heat it up and where to cool it down, that's definitely art. So what else in CNC machining that we've experienced in class is going to be impacted by stress and strain? So fixturing, yeah. And you can actually figure out how much cutting force you can allow in a certain operation based on how much friction force is available if you know how much the thing can deflect. Right? So you could work all those problems in series together. Maybe we'll do an example like that tomorrow. But what else in CNC machining is going to be important to us with stress and strain? So if we're doing a turning operation, and here's our workpiece, as the tool comes over and starts cutting, we're making cutting force, right? How does the part react to the cutting force? I mean, one thing is the chip flies off and we make the part smaller. But if we imagine the cutting's happening here and we're feeding in this direction, what direction are the cutting forces? You describe them as the axis or radial. So if we're feeding that way, there's some axial force, right, that's pushing it into the spindle or pulling it out of the spindle, depending on the angles involved, right? But there's some force that's aligned with the axis of the part, and there's some force that's aligned with putting radially towards the center of the part, right? So that cutting force that results, you could put it in components that line up with the axis and this axis. So what does the part want to do while we're clamping on it? So if I'm clamping it here and my hand is the spindle, and I can only do like a quarter rotation here, but it's trying to spin, right? The part doesn't want to spin. It's the spindle that's making it spin. The part wants to stop spinning when we apply a force opposite the direction of motion. So the part would like to stop spinning. So it's trying to spin slower than the spindle is. If we don't have sufficient clamping force, it will stall in the spindle and it will rotate in the spindle, right? So it could rotate in the spindle. It could slide in to the spindle, right? If we don't have sufficient friction. So if we don't have enough clamping force, we won't have enough friction. So let's say we've cranked up the hydraulic pressure. We've got plenty of clamping force, got a good friction coefficient. So it can't move into the chuck and it can't stop spinning. what does the part do then? I've still applied the force to it. It's still got that stress on it. It has to strain, right? So if I'm applying a force to it, part of it wants to compress. It wants to go into the thing. And part of it wants to bend. Can I bend this? I can. You see the deflection, right? So in addition to having stress keeping us, it's not the one. Oh, it's not in this presentation. That's okay. I know the equation. In addition to keeping us in place in the machine tool, the part wants to deflect. Anybody know what the deflection is related to? Anybody know what the equation is for deflection? After all that, there's only one person watching. What's that?
Hopefully it's him.
Hopefully it is. Maybe he gave up, left in disgust. Does anybody know how to calculate deflection? Yeah.
Isn't it like force times length?
All right, so we've got force. Can I write? I can't write on anything. I can write on my forehead. Force. All right, so force times what? Force times length. You guys agree that the force times the length is going to be important in figuring out the what length do you mean? I agree, by the way. Length is totally in the equation. Or I'm thinking of more the bending one. So from where we're supporting it to where we're applying the force, that's the length we care about, right? And so force times length. If force times length actually goes at the top of the division thing, right? Does that make it at the denominator or the numerator? It's not denominator or denominator. Numerator. Like, one of the most uncool things for any professor to do in a classroom is not erase the whiteboard when they're done with their class. It's like faculty training 101 is you're a jerk if you don't leave a clean whiteboard for the next faculty member. That one has been there for at least 3 weeks. Wonder if Emily and Jane and Stephanie and Abby and Isabella and Cody and Lucas and Danny know that they're famous. All right. So force times length. And then what goes on the bottom of the equation? So those are the factors on the top of the equation. Force times length. Maybe you know what goes on the bottom of the equation? Yeah.
Isn't it a constant C times E minus the elasticity times I for the moment of inertia?
Yeah, so I for the moment of inertia depends on the shape of whatever it is. So my arm elbow system here is going to have a different moment of inertia than yours because they're different diameters and probably different muscle strengths. I'm guessing you work out more than I do, but I don't know. But so we'll have a different moment of inertia there. And if it's a cylinder, which most of our turn parts are cylinders, then that moment of inertia is going to actually include the radius. And is the radius to the fourth power in the moment of inertia equation there for a round thing? I think it is. So the radius is really important because it's to the fourth power. That's all on the bottom half of the equation. The force times length, the length is cubed. So it depends on the diameter of the part, the material it's made out of, so the modulus of the material, and some other constants down there on the bottom. But the length cubed. which means the further away you are, the more impact that has, right? So if I'm applying that deflection force out here, it's going to have more impact than if I'm applying the same force in here, right? So what shape is the part going to be when it finishes? It's not going to be a cylinder, right? If we're deflecting it as we're cutting it, but the tool's moving in a straight line, then it's not going to be a cylinder. Is it going to be skinnier at the chuck end or fatter at the chuck end? The end where we're supporting it. Is it going to be skinnier or fatter? It's just a make you think question, isn't it? It's going to be skinnier at the end where you support it. Because as the part deflects, it moves away from the tool, which means your effective depth of cut is less at this end than it is at this end because it hasn't moved away as far at this end. So the part will be sort of half an hourglass shape to where you support it. What if that's unsatisfactory? What could you do in the machine to make that go away? Who was it that said we could reprogram our pocket to make it the right shape? So you could compensate in software. If you knew how much it was going to deflect, you could program it to have a deeper depth of cut at the beginning, a shallower depth of cut at the end. But that deeper depth of cut would also give you a heavier cutting force. So it's not going to be a linear relationship, but you could figure it out. You could compensate in the machining. What else could you do? In the machine. What else could you do in the machine? Yeah. So yeah, always choke up on the part as much as possible. Cut as close to the spindle as possible. Then you'll have less impact from the deflection. That's one thing. Scary when you're in close to the chuck though, right? Yeah. Who's heard the full helicopter crash? When the turret comes in contact with the rotating chuck jaws? It happened in one of the lab groups. You heard it? Were you the operator? Was it scary? Yeah, I was in my office about 40 feet away on the other side of a block wall. I heard it too. Yours might not have been the one I'm thinking of then. There was a really good one. By the way, if you're using the lathe and it suddenly sounds like a helicopter is flying in, just hit the E-stop, don't think about it. If you're on purpose doing an interrupted cut, so if you have a part that has a hole in it and you know that your tool is going to impact the hole, it could sound like a helicopter then. If you're expecting the noise, it might be okay. But if you're not expecting the noise, just hit the E-stop. So you could hold up closer, like choke up on the bat when you play baseball, right? Choke up on the part. What else would you do? You take smaller cuts, so reduce the cutting force. And so a lot of times what we do to control deflection is we keep the cutting force as low as possible. It also makes it so we don't have to clamp as hard if we keep the cutting force as low as possible. So when we cut plastic parts, we have to make, it's one of the reasons when we cut plastic parts, we have to make such small chips, is because trying to keep the cutting force down. What else could we do? You guys know physics pretty good. So I'm holding it here. I got to apply a force across it. Yeah. I could also hold it here. So some lathes will have what we call a tailstock. And often what you do is you'll drill a small hole in this end of the part. And your tailstock has got a point on it. And so you just drive that point into the small hole. And there's actually a hydraulic pressure that pushes it up against there to make sure it stays in. And then you're supporting it at both ends, which will then give you like a hump in the middle, right? It'll still deflect. It just won't deflect as much. And it'll deflect the most in the middle of the part instead of at one end. You could even overcome that deflection in the middle by using what we call a steady rest, which is basically a bearing that the part rides on that follows behind the tool on the other side opposite the tool. And it's like a little clamp thing that keeps the part pushed back up against the tool as you move along. That'll tend to burnish the part and things like that. It'll rub on the part. but it can reduce that deflection. So this stress and strain in CNC machining is really important to us, both from the fixturing standpoint. So because we get most of our fixturing from clamping the part and the friction. Also, it's important in understanding the deflection and how the part's going to change shape when we let go of it, when we squeeze on it, and as the cutting force is applied. All right. Does that make sense? You guys could calculate these things, right? We didn't tell you, because I didn't have my little write-on thing and there's no whiteboard, I didn't tell you the equation for deflection. But there's a quiz question that asks you to calculate how much something deflects. I guarantee there is. So you could say deflection of simply the head beam. Well, that one's not simply supported, right? It's supported at both ends. That one's supported at both ends. Simply supported just means you're only holding one end of it. That's what we mean when we talk about stress and strain. Those are all images. Deflection, slopes, beam calculations. Calcresource.com. That sounds like a credible website. Beam deflection tables. Mechanicalc.com. They must know what they're talking about. There's a YouTube video. Wikipedia. I'm looking for Reddit. Any one of these is going to have the equation. So you're supported at two ends. That's not the one. There's a lot of stuff there. Maybe it's cantilevered beam we want. You could also go to your stress textbook. There's the picture we're looking for, right? Except we're not applying that force all the way along. We're applying it at a point, but that doesn't matter. So there's your deflection. 8 times the elastic modulus. Oh, length is to the 4th power here. Why is it to the 4th power up there? Oh, because it's planar. That's right. Here's where we just have the one force. Is to the 3rd power. All right, so if you need to know deflection of a beam, you can look it up. If you need to know how much it's going to clamp and how much it's going to expand, you could derive that, right? When I asked if you all could derive it, you said you could. But you could go to the slides and you could look it up. I think if you look at the next presentation after this one, you'll see the slides for the deflection of a beam. All right. So today in the afternoon, I'll have up the quiz, this midterm quiz, we'll call it, midterm homework, we'll call it. It's unlimited submissions. We'll have a week to finish it. We'll talk about it in class tomorrow. So come to class tomorrow prepared to ask questions if you think you're going to have questions. But we have Tuesday next week, right? So we'll also have some time on Tuesday next week to talk about it, and I'll have it due at the end of the day on Wednesday, so we could even talk about it on Wednesday next week. Don't wait until the last minute to figure out what your questions are. It's way easier if you ask the questions earlier, and we do that earlier. And the other thing I was going to talk about today, and we only got 5 minutes left, so we'll keep this brief, and we'll do that tomorrow also. But we want to talk about the group project assignment. If you go to the slide for today's lecture, here, that's not today's. This one is the slide for today's lecture. And so if you click on this, you'll see us talking live right now. If you click on that one, you'll see us talking about this last week. We didn't talk about manufacturing economics yet. We'll do that tomorrow. But you'll also see a link to this group assignment here. And so the group assignment text is the same as I've done for the past couple of years, with the exception that you do not have to use the ME1800 Stirling engine as your part, right? At the beginning of the term, I told you that you could pick anything that you wanted to make, and you could even be like a job shop that's doing B2B sales. That was okay. Just pick the business that you want to do and then do that. If you couldn't come up with anything, or you're really bored with it and you want to, you can use the ME1800 thermoacoustic engine. And there's a simple bill of materials and stuff here that we talk about that. But the requirements for the thing to hand in is a business plan no longer than 4 pages. It's basically designed to convince me, the investor, that you understand what it's going to take to operate this business successfully and create the product that you want to create. And we'll go into that in detail tomorrow. But the cost to make the first part, that means what's it going to cost to get a leased facility, to get the machine tools that you're going to need to use, to get the tooling that you're going to need to use, to get any other things that you need to do that you have to do before you can even make one part. That's the cost to make the first part. The price points and sales projections, I don't want to do that. I guess you have to, in order to do the next one, you kind of have to do that. So decide how much you're going to sell and how much you're going to charge for it. You don't have to do any research to justify that. Just make it be something that sounds believable to you. And then how many you'll have to make, what it'll cost to make them over time in order to pay back what it costs to start the company and pay yourself over time. So that's there. We'll talk about that again tomorrow more as we talk about this general manufacturing economics topic. This will fit into that. And I'll go through some examples of the things that you're going to have to consider as you're doing this tomorrow. Anything else? How's labs going? Some people say good. Your lab group yesterday, because you were there yesterday morning, right? The day before, when I was leaving, so we don't have our lab staff both left this term, so we actually don't have any full-time staff working in the labs now. It's me and some students. The day before, on Monday, when I was leaving, the student who's supposed to come in the morning and set up, I thought Monday was Tuesday. I thought the next day was going to be Wednesday. We don't have lab Wednesday morning. So as I was leaving, I said, hey, and I don't know what time you're planning on coming in tomorrow, but you can come in late. Just get here when you get here. Don't worry about it. There's nothing to set up tomorrow. And when I was walking up the stairs and let you guys in, I still thought it was Wednesday. I'm walking up the stairs and I said, wow, there's a lot of people waiting to get in the lab at 9 o'clock this morning. Wonder what they're all doing. Oh, you know, most of them look really familiar. Huh. I unlocked the lab. Everybody walked past me and went to the classroom. That's when it dawned on me that it was Tuesday. We only started like 5 minutes late though, huh? It was pretty good. So sorry about that. But we get an interview this afternoon with somebody that might come in and take one of the positions that's open. And hey, if anybody's a senior and you're graduating, you want a job, full-time job here at WPI, there's an opening. You could be the lab technician guy person if you want to. I'm good for today. Unless you guys have any other questions, we'll see you here tomorrow. Same bat time, same bat channel.